Hello, today we're going to look at solving problems on the topic of solids and their elastic properties. And so the task is, we have two springs with a stiffness of 100 and 300 newtons per meter. What will be the stiffness of the spring system if we connect them in different ways? There are two main ways here. This is a serial parallel connection. These two methods will yield different results. So let's first consider, for example, a connection such as a series 1. To put it another way, we have two identical springs firmly hooked together by their two respective ends. So, for example, this is our spring with stiffness K1, and this is our spring with stiffness K2. And we load this system with a certain amount of force. So, in order to see how this system will behave, we apply a certain force. That is, let's say we hang some kind of weight, and we watch how this spring system will behave. Well, in this case, you and I can also say that the system consists of these two springs. We can replace it with a single spring that will provide the same resistance to the applied force. That is, specifically, a spring with some total stiffness, which we'll be looking for in this case. So what is this total stiffness equal to? To answer this question, we must look at how this system will behave in terms of deformation. Each of these two springs will stretch depending on its own stiffness. Moreover, we can say that the force applied to the first spring will be exactly the same on the second spring. This follows from Newton's third law. That is, with whatever force we act on the first spring, it resists with that same force. But simultaneously, it exerts the same force on the second spring. Accordingly, the same force arises in spring number 1 as well. Therefore, we can say that the resulting force that will work inside these springs will be the same, and it will be equal to the force that is acting upon this system. As for the extensions, each spring will stretch by different amounts under the same force. The spring that has less stiffness will stretch more. Accordingly, the spring with greater stiffness will stretch less. So it turns out that the total extension of this system, we can denote it as delta x. It will be made up of two extensions. Each spring contributes to the total extension of this system. And now our task is to write out all the extensions based on Hooke's law. So what is the total extension of the system? It's the ratio of the total force acting on this system to the total stiffness that this system has. So in this case, we'll denote it as the total stiffness in the first case. Here, we find that the extension of the first spring is the ratio of the force F1 that arose in it to the stiffness K1 of this spring. Similarly, in the second case. So, we've got this expression, and again, based on what we know about the equality of the forces in each spring and the total force acting on the system, we can divide everything by this value, which cancels out all the numerators. That leaves us with the expression that 1 divided by the total stiffness, in the first case, is 1 divided by the first stiffness plus 1 divided by the second stiffness. Now, to simplify the solution, let's find a common denominator for these fractions and add them together. To do this, we take the common denominator as K1 and K2. Using common factors, we get the sum of these stiffnesses here and their product here. And to find the total stiffness, we'll flip both the left and right sides. So it turns out that the total stiffness in the first case will be the product of these stiffnesses divided by their sum. Let's substitute the values and get the answer. So multiply 100 by 300 and divide by 100 plus 300, that is 400. We can cancel out two zeros here, and if we divide 300 by 4, we get 75 newtons per meter. So that's the stiffness for a series connection. As for the parallel connection, in this demonstration, we take two springs and begin the process of loading them in such a way that they remain parallel to each other at all times. To achieve this, of course, you could use a bar of some kind to pull on, but regardless, given they're parallel, we can say the deformation in these springs will be the same, meaning they'll stretch by the same amount. But at the same time, the force acting on the entire system starts to be distributed between these springs, depending on their stiffness, of course, and it's distributed differently. So, two elastic forces will arise, working against the total external force. Then, based on the balance of this system, we can say that the total force is the sum of the two forces that will arise in each spring. Now we just need to expand each of these forces. What is the total force acting on the system? It's the total elastic force acting in the opposite direction. And that, in turn, is the total stiffness, but for the second case now, multiplied by some delta x, which is the system's deformation. And we'll write the same thing now for each individual case. Here we get k1 times delta x, and here k2 times delta x. As we can see, delta x, the deformation of this system, will be the same throughout, because these springs are in parallel. So, we can get rid of this value here by reducing it, and we get the answer that the total stiffness of such a system, when connected in parallel, is the sum of these stiffness values. That's 400 newtons per meter. Therefore, we conclude that when we connect several springs in series, the overall stiffness will decrease. In parallel connection, the stiffness increases. This property is often used in device manufacturing that operate using springs or other elastic cords that have the property of elastic deformation. That's all for me for now. See you. Goodbye.